This is the video for exam practice session 7, which is covering decision networks and HMMs. Before we start on the problems, let's first talk about a few key terms for decision networks that will be useful in the first problem. So the first is what's denoted as EU of A, and this is the expected utility of taking some action A. Next, there's also the term MEU, which is the maximum expected utility. So this is simply the max over all the actions you can take of your expected utility of A. Lastly, there's also VPI, and VPI is your value of perfect information. And what this means is it is the value of acquiring some new evidence, and we'll denote that new evidence as E prime, given that you already knew some information, some evidence, and we'll denote that as lowercase e. And mathematically speaking, this is equal to the maximum expected utility knowing both E prime and E minus the maximum expected utility if you only knew E. And so what this value represents is the expected value that we get if E prime is revealed and then we act. And some of the properties of VPI is that VPI is always non-negative, so it's greater than or equal to 0, so the value of acquiring new evidence is always either going to be positive or it's going to be 0. And in the case it's 0, that means that your maximum utility hasn't increased and you haven't gained any information that will help you increase your utility. Another property of VPI is non-additivity. And this is simply that VPI of A plus VPI of B does not equal VPI of A and B. And the last property is that VPI is order independent. And what this means is if you have VPI of A and B, given that you knew C before, this is always equal to the VPI of A given C plus the VPI of B given both A and C. And this is also independent to the case in which instead of first seeing A, we first saw B given C plus the VPI of A given that we already got the information B and C. So regardless of the order that you get if you get A first and then you get B versus getting B first and then getting A, the VPI that's equal to the VPI of A and B, and that's independent of the order in which you received that information. Okay, with that, let's move on to the questions. So in this first question, we're trying to figure out your expected utility, and the case is that you have some action, and Pac-Man has to decide whether to accept the challenge or to decline the challenge. And the challenge is the game of a coin flip. So the coin flip is the variable h, and it's a fair coin, so it's a 50-50 chance of being heads or tails. Then we know that if Pac-Man accepts the challenge, then he will have certain utilities based on the outcome, and if Pac-Man declines the challenge, then he will also have certain utility values based on the outcome of the heads. So first, let's calculate the expected utility of accept. So what this looks like is you're just going to look at both of your possible values of h, all your possible outcomes. So you're going to technically sum over your values of h, of the probability of h times the utility of that value of h and the action accept. And so what you get is you get 0.5 times 100 in the case that it comes out heads, and then 0.5 times negative 100 in the case that it comes out tails. And so if you do some algebra, this comes out to 0. Now let's compute the expected utility of declining. So in this case, we have the same exact equation, except this is now the utility of h and decline. So what we get here is if it's heads, which has a 50% chance, then we get a expected utility of negative 30. And if it's tails, which happens with a 50% chance, then we get an expected utility of 50. Or we get a utility of 50. And so the expected utility is equal to negative 15 plus 25, which is equal to 10. So now we want to compute the maximum expected utility with no information about heads, and this is simply the max over the two possible actions that we can take, which is accept and decline. So this is the max of 0 and 10, which is equal to 10. And the last question is asking, what is the action that achieves this maximum utility? And we can just look back at how we got to 10, and we see that the action is decline. So the action that Pac-Man should take to maximize his expected utility is to decline the offer. Okay, now let's look at the second part of this question. So now we have some fortune teller observations, and we're in the same case where Pac-Man has to make an action about whether to accept or decline, but there's additional information that's coming from these fortune tellers that know something about the outcome of heads or tails. So in part I, we actually have the case in which the fortune tellers give perfect predictions. So if it comes out heads, then the fortune teller will say that it will come out heads, and if it comes out tails, then the fortune teller will say it will come out tails. So the fortune teller knows the exact outcome of h. So in this first case, we want to know whether or not VPI of O1 and O2 is greater than or equal to VPI of O1 and VPI of O2. And this turns out to be not to be true, because the VPI of O1 means that we know exactly what heads is, and then we get some utility from knowing the actual outcome. And then, however, VPI of O2, given that we already know O1, is going to be 0 because we don't gain any information. There's no nothing else we can do to increase our utility. So in this case, VPI of O1 and O2 is actually equal to VPI of O1 and also equal to VPI of O2. So in this case, this right side of the equation is actually equal to double the left side of the equation. It's actually greater than the left side of the equation. So this statement is false. The next statement is saying that VPI of OI for some I is equal to VPI of OJ for a j not equal to I. So the VPI of a fortune teller given his or her prediction is the same as the VPI of a different fortune teller giving the prediction. And because these probabilities are the same for all fortune tellers, and because therefore this problem is symmetric, then this case does hold, and this is true. So let's mark in this bubble. Okay, now moving on to this third case. So here we actually know exactly what these values are. So if we know one fortune teller, O1, we know what that fortune teller gives, then we know exactly what H is. So O2 doesn't give us any additional information about how to increase our utility. So therefore, VPI of O2 given O1 is equal to 0. And for the same reasons, VPI of O3 given both O2 and O1 also doesn't give us any additional information. So this also is equal to 0. So it's not true that the left-hand side is greater than the right-hand side because they're equal, they're both equal to 0. So this statement is false. Lastly, let's look at option 4. So in this case, we have the VPI of knowing the variable h, and because in this case the fortune tellers give perfect predictions, then knowing one of these values or knowing all of them, or any number of these values of O, means that we know exactly what h will be. So therefore, the VPI of h is equal to the VPI of O1, O2 through On. So therefore, this statement is also false. And that's our final answer. Next, let's look at problem 2. So in this case, the fortune tellers are pretty good, but not perfect, and they aren't giving us perfect information. And we're asked about the same 4 statements as above. So in this first case, we have VPI of O1 and O2 compared to the VPI of O1 and the VPI of O2. So to approach this problem, let's first expand out what this is. So VPI of O1 and O2, VPI of O1 and O2 is equal to VPI of O1 plus the VPI of O2 given O1. Or you could also say, because of the order independence, you could also say that this is equal to the VPI of O2 plus the VPI of O1 given O2. So we also know that in this case, where we have these fortune tellers, that the VPI of O1 is going to be strictly greater than the VPI of O2 given O1, and also that basically VPI more generally of a single fortune teller OI is going to be greater than the VPI of some fortune teller OJ given another fortune teller OK. Because the first fortune teller that we get, before that we know no information, and we're essentially, when we get that first fortune teller prediction, we're essentially getting a sample, we're getting some information about H. And then when we get a second prediction from another fortune teller, that's like a second sample. And because we already have a single observation from the first fortune teller, when we get the second fortune teller, that tells us we get a little bit less information than the amount of information that we got from the first fortune teller. So for this reason, we know that VPI of, so we're trying to, going back to this statement, we're trying to compare this value right here to this value right here. And VPI of O1 is equal to the VPI of O1. However, VPI of O2 given O1 is less than the VPI of only getting O2 versus getting O2, only getting O2 given that you already knew O1. So therefore, the left side of the equation is actually going to be less than the right-hand side of the equation because VPI of O2 given O1 is less than VPI of O2. So this is incorrect. Next, let's look at this second case. So here we have VPI of OI is equal to VPI of OJ. Similarly to the first case, because all of these fortune tellers have the same exact probability distribution over the fortunes that they will give, and because we actually don't know the outcome of what OI is or what OJ is, the expected amount of information and the value of perfect information that we're going to get from OI is equal to the value of perfect information of OJ. So this answer is correct. Next, let's look at the third case. So here we have the VPI of O3 given O2 and O1 versus the VPI of O2 given O1. So this case is similar to what we talked about in the first case, where when you the first observation you get will give you the most information about your utility, and each time you get another sample, you'll get you will get additional information about how to increase your utility, but the amount of information that you gain for each additional sample is going to decrease, because as you gain more samples, you know more and more about, and you have more confidence about what H is equal to, and therefore there's less information to be gained from just a single sample. So for this reason, when you have VPI of 0.2, given that you know 0.1, the value of this perfect information is going to be greater than the value of perfect information in the case in which you already know 0.2 and 0.1 and you're getting a third sample, 0.3. So this statement is incorrect. Next, let's look at the third statement. So in this case, we have the VPI of heads and we have the VPI of 0.1 through 0n. So since our fortune tellers are not perfect, and when we get n observations, we're not guaranteed to know the value of H. And we're not, and we certainly will not know the value of H with 100% accuracy. So therefore, the VPI of knowing the value of H is going to be strictly greater than the VPI of all of the observations of all the fortune tellers. So this statement is true. And that's the final answer. Now let's move on to question 3. So this case is slightly different, and we have some new variables m, and each of these m variables are the mood of the fortune teller. And if the fortune teller is in a good mood, then the fortune teller's prediction is guaranteed to be correct. And if the fortune teller is in a bad mood, then the fortune teller's prediction is guaranteed to be incorrect. And you have some prior on their mood, namely that they're going to be happy with some probability 0.8. And these fortune tellers are the same as the fortune tellers in part 2, in that they do not make perfect predictions. So let's look at this first case. So this is saying that the VPI of M1 is greater than 0. And so the way we can look at this is we now know the fortune teller, we get some piece of information and some evidence, and that is the fortune teller's mood. However, when we get this, we don't know anything about what their prediction was. So while we might know that their prediction is guaranteed to be correct or guaranteed to be incorrect, we don't know what their observation is, and therefore we don't have any additional information about H, and therefore we cannot increase our utility because we don't know anything. We haven't gained any information about H, and thus haven't gained any information about how we can increase our utility. So that answer is incorrect. Now let's look at the second the second statement. So in this case, we have the VPI of M1 given O1, or MI given OI for all I. And this is the case in which you know the observation or the prediction of one fortune teller, and you are getting a new piece of information, and you want to know the value of getting a new piece of information of the fortune teller's mood. And because the fortune teller, we aren't certain about whether or not that fortune teller's prediction is correct, then getting the mood will tell us whether or not that will basically tell us the exact information of whether that prediction is correct or incorrect. And with that information, we can infer the exact value of H. So this VPI is guaranteed to be positive because it will give us information about H. And it'll actually give us the exact information about H rather than just some estimate of H. So this answer is correct. So now let's look at the third option. So in this case, this is actually very similar to the first case. We said before that the VPI of M1 is equal to 0. And this actually doesn't change for any of the moods. So if you have a mood of any fortune teller, but you don't know their prediction, that doesn't tell you anything about H. So you can't increase your utility, and the value of perfect information is going to be 0 because it doesn't tell you anything about how you can increase your utility. So even if you know all of the moods of all the fortune tellers, that doesn't give you any information for increasing your utility, so therefore this is equal to 0. So these are both equal to 0, so they are equal and not greater than, so this answer is incorrect. Now let's look at this final statement. So in this case, we have VPI of H, and we want to compare that to the VPI of MI and OI. So in the first case, we have ground truth information about H, and that gives us some ability to increase our utility and pick the correct action. And in the second case, we have the mood and the prediction of the ith fortune teller for all, and we want to consider this statement for all I, not just for one in particular. So in this case, if we have the mood and the prediction for one of the fortune tellers, then we know exactly what H is, because if the mood of the fortune teller is happy, then you know the prediction is correct, and then you know H is equal to the prediction. However, if you know the mood is unhappy of that fortune teller, then you know that their prediction is incorrect, and therefore you also know the exact value of H. So therefore, regardless of which fortune teller and mood you have, as long as I is equal to I, this statement is correct because the information about the mood and the prediction is the same as the information you gain from knowing H. So this is true. And that is it for question 1. Now let's talk about question 2. So in this case, we are considering the forward algorithm for an HMM. And we can see up here that the standard forward algorithm update is written right here. And something to keep in mind is that in general, the goal of the forward algorithm is to determine the probability of a state X at a time t, given all of the evidence up to that state. So the goal is to find, probability of xt given E1 through t. And this is just shorthand notation for E1, E2, E3, all the way up to ET. And you want to be able to do this for some arbitrary t. And the way you can do this is iteratively, and first starting at the first time step, computing probability of E1 or X1 given E1, and then using that probability to update it with both your transition probability distribution, which is known from the Bayes-net right here, and the emission model, which is given by this arrow right here. So what we do is we start with the belief at the previous time step, and then multiply that by the transition. So this is the belief actually at t minus 1. This is the transition distribution. And then we sum over all of the possible values that xt minus 1 can take on. And then we take that and multiply by your emission model or your observation model, which is the probability of your evidence given your current state. So now what we want to do is extend this algorithm, the forward algorithm, to different structures and extended variations on HMMs. So in part A, we have this new Bayes-net, and in this Bayes-net we can just tell from the very beginning that we have the same transition probability distribution as before, which is going to be the probability of xt given xt minus 1, and that's given by this arrow right here. However, our emission model has changed. So instead of having just the probability of ET given xt, we know just from Bayes-nets that we always have the CPTs of a node given its parents. So we have, the probability of ET given the probability of xt and xt minus 1. And we have these, both of these for all t, but that these transition probability distributions is the same for all t, and this emission model is also the same for all time steps. So now what we want to do is complete the update. So what we have right here is our belief at the previous time step, and we want to update the rest of this. And actually, before we jump into this, let's talk a little bit more about the equation up here. So the reason why we get this update equation is we have, the goal is to compute this value right here, and this value is proportional to the case in which you're not conditioning on all of the evidence, because the reason why it's proportional is if you have the probability of xt given e1 through t, this is equal to the probability of xt and e1 through t divided by the probability of your evidence. And you can think of your probability of your evidence as a constant factor because you already have observed this evidence, and so it's not, this is just some constant. And so therefore these are proportional, and then once we go through all the updates and we have determined what we're proportional to, then at the end of the algorithm we can normalize. So, and then the reason why we have this update from here is that this entire, this thing inside here, this is equal to the probability of xt minus 1, and e1 through t minus 1. And then when you sum over all of the values of xt minus 1, then you're marginalizing out this variable, and the result is the probability of xt and et minus 1, and e1 through t minus 1. And then finally you will multiply this by your emission model probability of et given xt, and that will give you the probability of xt and your evidence all the way up through t instead of t minus 1. And the reason why, note that to write this, we have to make the conditional independency assumptions of the HMM model, namely that conditioned on the current state, the current observation and the future states and observations are independent of the past. So with that in mind, let's talk about this part A. So here inside the sum, the whole right side of the equation, we want to be equal to the probability of xt plus 1, and e1 through t. Because then we're going to be marginalizing out. Actually, so this should be xt minus 1, not xt plus 1. Not sure if I can fix that. And then we're going to be marginalizing out xt minus 1, so the result will be xt and e1 through t, which is just exactly what we had up here. So in order to get this probability distribution, we start with our previous belief, and then we want to multiply first our transition model, which is the probability of xt given xt minus 1. And so in this case, this will now give us the probability of xt minus 1, and e1 through t minus 1. And now we want to also incorporate our current evidence, which is et. And the way we can do that is simply just by multiplying the probability of et given xt and xt minus 1. Note that I was careful to make sure that all of these indexes were correctly lined up. So these are given xt minus 1, and then we're multiplying probability of xt minus 1 and et through 1 minus t minus 1, and so on and so forth for this part as well. And that is the final answer. So next, let's look at part B. So in this case, like before, we can just look at what our new transition and emission models are. So our transition model, again, is actually going to be the same. So it's just the probability of xt given xt minus 1. However, our emission model has changed again, and now it relies not only on the current state, but also on the evidence at the previous time step. So our emission model is going to look like ET given both ET minus 1 and XT. So back right here, we're starting off with our belief. And then in order to get a value in here that is equal to the probability of XT and XT minus 1 and E1 through T, we're going to multiply our belief at the previous time step by both our transition model, which is xt given xt minus 1, and that will give us this term right here, and by our emission model right here, and that will give us the additional ET instead of having only E1 through ET minus 1. So the answer is the probability of xt given xt minus 1 and the probability of ET given ET minus 1 and XT. Okay, now let's finally look at part C. So in this case, we're actually looking for something slightly different. We're actually looking for the probability distribution of the last of two states, xt and xt minus 1, given all of your evidence up to 1 through t. And your past belief is the probability distribution over these two states, and the evidence up until time t minus 1. So first, as before, let's just look at what CPTs we have available to us, and that's going to be our transition model, which is xt, and xt is going to be dependent on xt minus 1 and xt minus 2, because those are its two parents. So we have xt minus 1 and xt minus 2. And then our emission model is actually just the typical emission model. So we have probability of ET given the probability of XT. So now what we want to do is this value inside the sum, what do we want it to be equal to? So we want it to be equal to, we want to be able to get to this right here, and after we have marginalized out xt minus 1. So inside the sum, we want something that is equal to xt, xt plus 1, and xt minus 1, as well as all of the evidence. So that when we marginalize out xt minus 1, we get the probability of xt, xt plus 1, and E1 through t, which is proportional to the probability of xt and xt plus 1 given E1 through t. And so in order to get this joint probability distribution, we can take our past belief and then multiply that by our transition model. And in this case, we want to be careful with, this is actually not the correct form because we want to have xt and xt plus 1. And in our final equation, so we want, and we have xt and xt minus 1. So we want to put here the probability of xt plus 1 given xt and xt minus 1. So then when we multiply these two together, we'll get the probability of xt minus 1, xt, xt plus 1, and E1 through t minus 1. And then in order to also incorporate the last variable in this joint distribution, we need to incorporate our emission model to get ET. So that's going to be probability of ET given XT. And that is the final answer. Now, let's look at question 3. So in this question, we are trying to determine the most likely estimates for HMMs. And the thing to remember is that when you're running the Viterbi algorithm, the goal of most likely estimates is to find not some probability distribution, but the argmax over your sequence of states x1 through xt, of the probability of that sequence given all of the evidence that you saw. ET. So instead of finding some probability distribution at some time step, given the evidence up to that time step, you want to find the most likely sequence of states, sequence of hidden states that the most likely sequence of hidden states given the evidence that you saw. And actually, the shorthand for this would be, the argmax of the probability of x 1 through t given e 1 through t. This is exactly what the Viterbi algorithm computes. And the way that it computes it is using dynamic programming, meaning that instead of keeping track of looking at all the possible sequences of states, it keeps track of the maximum sequence of states so far up until some time step t, and then uses that to compute the next maximum most likely sequence of states up to xt plus 1. And this is what your update looks like. So it looks pretty similar to the forward algorithm in that you have your transition model and your emission model. However, and you also have this previous state, which is similar to your belief in the forward algorithm, except it's actually more like the maximum estimate up to t minus 1. And then instead of summing here, we're actually going to take the maximum over all possible values of xt minus 1. So in question A, we want to figure out which of these probability distributions are going to be maximized by the sequence of states that's returned by the Viterbi algorithm. So basically, that's exactly what we have up here. So we are interested in the probability distributions down here that are equivalent to maximizing the sequence of hidden states given the sequence of evidence. So first, let's look at this option. This is saying that the Viterbi algorithm would be maximizing the probability of hidden states. However, it's not taking into account any evidence. So this is actually incorrect because this distribution is going to change based on the evidence and the observations that you have of your states. Next, let's look at this example. So in this case, it's actually only looking at the last time step as x capital T given E capital T. And this also isn't what the Viterbi algorithm is maximizing over because of the dynamic programming updates. And it's actually considering all of the time steps and all of the evidence, not just the last state and not just the last evidence. So this is also incorrect. And it's very much possible that if you were to maximize and find the most likely state x capital T given E capital T, that would be different than the xt that you would find if you maximized over the entire sequence of states given your entire sequence of evidence. So now let's look at this case right here. This is exactly what we have written up here. It is maximizing the probability of hidden states given the probability of your sequence of hidden states given your sequence of observations. So this is correct. Now let's look at this one. So we know that this is equal to the probability of x 1 through t given e 1 through t times the probability of e 1 through t and let's close these windows. So that means that this because probability of your evidence is a constant, therefore then this expression is proportional to the probability of x1 through t given e1 through t. So therefore maximizing this quantity is the same as maximizing this quantity. And so this answer is also correct. Okay, now let's look at this fifth option. So here we have the probability of x1 times the probability of e1 given x1 times the product of your observation models and your transition models. And because of our Bayes-Net structure in an HMM, this is actually exactly equal to what you have written over here, because this is right here. This is probability of E1 and X1, and then you next get E2 given E1 or X2 given E1, X2 given X1, and E2 given X2, and so on and so forth. And because you have these conditional independencies here, this is exactly the joint distribution of probability of all of your evidence and all of your states, your sequence of states. So this is also correct. And finally, the last option is exactly equal to this first option right here, because you're just taking your probability of your first state and you're taking the probability of the next state given the previous state. So this is just simply the probability of x1 through t for the standard Bayes-Net, or for the standard HMM, not for the standard Bayes-Net. So because you're not taking into account your evidence, this is also incorrect. Okay, so now let's look at part B. So in this case, we're getting variations on the HMM similar to question 2, except in this case, we want to compute a different update. So in part I, and we'll go right here, in part I, we have a new HMM where instead of just having states and observations of those states, we also have actions. And the actions affect the states. So your action at a current time step will affect the state at that current time step. So as above, let's first write down the conditional probability tables in this Bayes-Net that we are given. So first we have the probability of ut, the probability of u at a given time step. Then we also have the probability of xt given the parents of xt, which are going to be xt minus 1 and ut. And then finally, we also have the probability of ET given XT. So we want to use these to compute the most likely sequence of state and actions. So we now have a update that is a function of both XT and UT. So the goal is to find the most likely sequences of states and actions given the sequences of observations. So what we're going to start out with is when we're trying to compute this, we're going to have mt minus 1 of xt minus 1 and ut minus 1. And then what we want to do is to take into account, this is going to be the most likely sequence of, this is going to be the most likely, representing the most likely sequence of state and actions up until xt minus 1 and ut minus 1. And the probability of those for a particular state and action, state action pair, xt minus 1 and ut minus 1. So what we want to do is maximize over this previous time step to compute for the next time step. So we have max over xt minus 1 and ut minus 1 of, first we can just simply put in this value mt minus 1 of xt minus 1 and ut minus 1. And then we want to take into account the next time step. So say that we're right here and this is t minus 1 and this is time step t. Then we want to take into account the transition, the prior on u, and the probability of your observation, et, given xt. So first let's start with probability of ut. So the ut doesn't depend on the previous state or the previous action, so we can put that out front. So we get the probability of ut right here. Next, let's look at this right here. So this depends on the value of xt minus 1. So we need to put this inside our maximum right here. So we're going to get the probability of xt given xt minus 1 and ut. Then finally, we also have our emission model, which is how we're going to be incorporating our observations into this update. And because ET, given your current state xt, doesn't depend on the previous state or the previous action, we can put that right out here. So we have ET given xt. All right, now let's move on to part 2. So here we have a similar case, except where we're trying to maximize over 2 variables. However, we have a new HMM. So in this case, let's first start up by writing our Bayesnet probability tables as before. So we have just simply our transition distribution, which is probability of xt given xt minus 1. We also have a distribution for the variable ft, which is ft given xt, and then we also have the probability of our observation given xt. So now we want to maximize over the most likely sequences of states and the most likely sequence of unobserved emissions, given the sequence of observations E1 through T. So this update, as before, is a function of both variables, xt and ft. And what we're going to be doing is maximizing over the previous time step. So maximizing over xt minus 1 and ft minus 1. So, and we also we can take into account our update from the previous time step, which is going to be xt minus 1 and ft minus 1. So now let's take into account our current time step and how we got to our current time step. So first we have our transition model, which is xt given xt minus 1, and that's going to go inside the max right here, given xt minus 1, because it's a function of xt minus 1. Next we have our distribution of the emissions that it will make, and this is not a function of xt minus 1 or ft minus 1, so we can put it outside the max. So we have ft given xt, and then finally we have our observation model, et given xt, and this is also not a function of xt minus 1 and ft minus 1, so we can again put it outside the maximum. So this is et given xt. And that is the final answer.